Right, diverging lens only gives you virtual, upright, and smaller images, no matter how far away you are from the lens. I mean, how far away the object is from the lens. You will always see a smaller, upright, which is virtual image. That is the type of lens used by people who are short-sighted. That's why their eyes look tiny when you look at them. Anyway, so the idea is the same as before. Parallel through the focal point, but remember it's a diverging lens. So it, instead of focusing in the focal point, instead of going like this, it diverges out as if it had come from the focal point. So this type of lens behaves exactly like a convex mirror. You can think about it, it's the convex mirror, that's the surface of it, like boom, 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 like popped out. The second light ray would have gone through the focal point and then goes parallel, but I'll just go for the central one, the one that goes smack through the middle. So the refracted light rays, this light ray and that light ray, never cross, but your brain does this, and you see an image which is virtual, upright, and smaller, no matter, again, no matter how far away the object is from the lens, always the same story, virtual, upright, smaller. A couple of examples. 45 centimeter object is viewed through a diverging lens and appears to be 15 centimeters. Duh, obviously, since it's a diverging lens, it will always be smaller. The object is 25 centimeters away, that's dou, and we need to figure out the focal length of the lens. So magnification, we know that magnification is going to be 1/3, because it's 15 over 45, it's a real image, so it's upright. 1/3, I'm going to substitute negative di over dou is 1 over 3, di is negative dou over 3, and I use the focal length equation again. So 1 over f equals 1 over dou, and I flip, I have to add di, which is negative dou over 3. So same story. In this case, so you have 1 over f equals negative 2 over dou, and we know that dou is 25 centimeters. From there, my focal length is negative 12 centimeters, 25 centimeters. Just like a convex mirror, this lens has a negative focal point because instead of focusing, light rays appear to have come from the focal length, but they did not really come from that focal point. All right, another example. Let's say we have a 45, again, the same object is viewed through a diverging lens with a focal length of 10 centimeters. If the object is 15 centimeters away from the lens, how tall does it appear to be? So how tall is the image? So high is our question. So I'm going to first use, since I don't know height or di over dou, I don't know my magnification, but I do know my focal length, and this is misleading a little bit because I'm saying 10 centimeters, but since it's a diverging lens, you know that it's going to be negative 10 centimeters, or I hope you know. Anyway, so 1 over negative 10, that's 1 over f. Di is what we don't know, dou is what we do know, it's 15 centimeters. So 1 over 15 plus 1 over di equals 1 over negative 10. From there, 1 over di is negative 1 over 10 minus 1 over 15, common denominator is 30, so negative 3 over 30 minus 2 over 30, that gives you negative 5 over 30, which then, when you rearrange this, gives us di as negative 6, because 1 over di is negative 1 over 6, so di is 6 centimeters. And then we need to figure out the height of the image. So magnification is negative di over dou, di is negative 6, so negative over negative 6 over 15 equals high, which we're looking for, over 45, that's ho, the height of the object. Crisscross, applesauce, you get 18 centimeters is your height of the image. It's upright, so therefore it's positive, and it is tiny, well, smaller than 45 centimeters. That's it.